Welcome back to today's lecture on vector calculus. We're going to continue our investigation. In the previous lecture, we introduced the idea of a vector field. Okay? Now, the basic idea with a vector field is that you input a vector and this vector field outputs another vector. Okay? So this is the basic loose description of a vector field, but geometrically this is what we have. So at any point in space there is a vector associated with that point, which we denote by the vector f of x. All right. Now today we're going to look at the so-called divergence of a vector field. At the end of the last lecture, I said, okay, well, we're investigating a subject called vector calculus here. Now, calculus would seem to imply that we use derivatives or integrals and things like this. But for vector fields, it's not always clear what we mean by derivative. Okay? You've seen a number of ideas with what you've seen at school and also in multivariable calculus. But today, we're going to broaden the idea of a derivative. Okay, in a sense. And it's known as the divergence. Okay, well, think back to when you learnt about the gradient, grad f. Okay, so f is a scalar field here. It might be a function of 2 or 3 variables. And you were taught about the gradient of a scalar field. So just to remind you, for a function of 3 variables, the gradient acts on this scalar field, little f, and produces a vector field. Okay, this is a vector field here. Right? Okay. Now, to discuss this divergence, I think it's probably a good idea to introduce some notation for this so-called del or nabla operator. Okay? Now, it's a vector differential operator, and it's defined in the following way using these partial differential type of operators. Okay? And it's not really a vector, it's a so-called symbolic vector. Okay? And in words, we refer to this as the del operator or nabla or just del. Okay? All right. Now we can relate the divergence of a vector field with this del operator. And you can see here that this looks like a dot product or a scalar product. Okay? So the divergence of a vector field f is just the dot product of this symbolic vector with the vector field. Okay? Okay, so you can see, hopefully, that we've defined the divergence of this vector field as this bottom line. But we can write it compactly using the del operator and the dot product. Okay? Okay, all right. Now, as I said before, we can think of the divergence of a vector field as a type of derivative. Okay, now derivatives usually measure rates of change and things like this. So what does this divergence measure? Well, we'll get to that in a minute, but an important thing to note the divergence it acts on a vector field F and it produces a scalar field, right? All right, so that's very important. Also, you need to be careful about when the divergence is defined and when it's not. I say, okay, so let's say phi be a scalar field. Is the divergence of phi defined? Okay, what about the following? So here's some questions for you. Is the divergence of a vector field equal to the vector field dotted with nabla? Is it? Is it? Well, I'm not sure if it is, actually. This will be a scalar field, and this will just be another operator, right? So the bottom line the answer is no, okay? So with these new types of operations, we need to be careful about when things are defined and when they are not defined. All right. All right, let's do some calculations and actually work out the divergence of a few of these vector fields. Okay, so by the definition of divergence, notice here the vector field is only in the plane, in the xy plane. Okay, we can still talk about divergence for that. Okay, so for our problem, it's just the following. Okay, so now those partial differential operators operate on the components of the vector field F. So this operates on this. This operates on this, and we add, just like we would in a normal dot product, right? So we should get something a little like that. Now, notice our final answer is a scalar field, right? It's a scalar valued function. It's not a vector. Okay, so let's have a look at the other part B. in this case, what's it going to be? It's going to be something like this. Okay. So now we just go through, work out the corresponding partial derivatives and add these things together. All right. So see again that we've produced a scalar field here. Oh, sorry. Let me... Okay. Sometimes this is what happens in mathematics. Make a mistake, slightly change the problem. Okay, sorry about that. Okay. All right, so assuming we can do our partial derivatives correctly, then there's no real problem. All right, so here we're given a vector field in the plane, and we're asked to calculate the divergence at a particular point. All right? So all right, so again, just go through, work out the partial derivatives, and all right, so that's the general expression for the divergence. So that gives you the divergence at any point in the plane. All right, notice that the divergence for this example, it doesn't depend on the x value, but it does depend on the y value, right? So let's work out what the divergence is at the point in question. The divergence is going to be something like 1 plus 4. Now, notice in this solution I've mixed up the notation. Right? Up here I've used the del operator and the dot product, whereas down here I've just written out div f. Now you need to be comfortable with both kinds of notation. That's why I'm giving you both kinds. All right? You will see both kinds in exams or in your textbook or in the notes. So you need to be careful with. You need to be familiar with both kinds of notation. All right. So we've got an answer of 5. What does that mean? So what? What does it mean? Well, before we get to that, let's talk about some identities. If the divergence is some sort of derivative, then does the divergence obey the same kinds of identities that the derivative, for example, that we learnt at school obey? Is there a product rule? Is the divergence, are there any type of additive laws? Okay? And the answer is yes, but sometimes with a little bit of a twist. Okay, you can see in the top line, the divergence of two vector fields added together gives you the divergence of the first plus the divergence of the second. No problem there. The second line, it could be thought of as a product rule. Okay? Here the phi is a scalar field. Right? So here we're multiplying a scalar field with a vector field. And you can show that, well, yes, there is a product rule, but it's in the following form. Right? You can also use the third identity to simplify calculations. So if you take the gradient of two scalar fields, say phi and psi, and you cross them together and take the divergence, then you get 0. Right? That's a useful identity. When you're doing long calculations, it's very frustrating to do all the calculations and then come out with something like 0. Well, maybe there's an identity for that. Now, finally, some of you may have heard of the Laplacian operator before. Okay, this is a type of operator that pops up in the study of partial differential equations. Okay, now the Laplacian operator, it is just div grad of some scalar field. Okay, in this case, div grad phi. Okay, so how do you prove these? Well, if we've got time at the end, I'm going to come back and prove. I think I'll prove the product rule, but the other ones are easy to prove in a component-wise fashion. Okay. Now there is a way of proving a lot of these identities from vector calculus very quickly, and it's called the Einstein index notation. Okay, has anyone heard of it? Index notation? Okay, Albert Einstein once was asked, what is your greatest achievement in science? Okay, and he said, index notation, which is a way of simply writing complicated sums. He said, that's my greatest achievement. Forget about a theory of relativity and all this sort of stuff. My index notation. That's my crowning achievement. Okay, all right, so we'll come back to those if we have time at the end. All right, so I said before, what does divergence mean? What does it mean? Well, loosely speaking, you can think of the divergence as measuring the spread of a vector field. Okay? How much, like if I calculate the divergence of a given vector field at a particular point, loosely speaking, that number gives me a measurement of how the vector field is spreading away from that point. Okay? So we can measure it by looking at the flux or the flow out of a small closed surface surrounding P, like a box or a square or a circle, a sphere. Okay? So have a look at this particular example. Some of the vectors have been drawn in for, say, a given vector field. And we've also drawn in there a sphere and a box, and they have the same centre. You can see here that there's really only outflow out of that sphere or box. The vector field is just flowing out of that box. All right? So in this particular example, you would think, okay, well, the divergence at any point within in that sphere of this vector field, the divergence is positive. Okay? All right. Now we'll prove that a little later. But let's get down to a little bit more interpretation. Suppose that F is a vector field that measures the velocity of a gas or a fluid. Right, then the divergence of F represents the rate of expansion per unit volume under the flow of the gas or the fluid. If the divergence is positive at a point, then there's a net outflow of any small closed surface enclosing P. So you can say that gas is produced at the point P, and we say the gas is expanding. On the other hand, if the divergence is negative at a point P, then there's a net inflow of any small box or sphere containing the point P. All right? And you can say that gas is consumed, and we say that the gas is compressing. Now, what happens if the divergence is 0? Well, it's not compressing or expanding. And if it's, say, a fluid, we would call this type of case an incompressible fluid or incompressible gas. All right, so here's some pictures, just to reinforce what I've said. So here's, I guess we're working in the plane here. All right, so at this point, the gas is expanding and divergence is positive at that point. We call that a source point. And down here, you can see that, well, at this point, the divergence is negative, so the gas is compressing at that point. Okay? All right, well, you can also understand this in the following context. If the divergence is positive at a point, then as the fluid moves, the volume of any small closed surface enclosing the point P, the volume increases. And if the divergence is negative at the point P, then the opposite happens. All right, so let's do an example and see how this all works. All right. Here's a following diagram of a vector field in the plane. Some of the vectors have been drawn in. And we're told that this vector field V is a velocity field. And we're asked to calculate or find where the divergence is positive and where the divergence is negative. So really all you need to do here is look for expansion or compression. Where there's expansion, the divergence will be positive. Where there's compression, the divergence will be negative. Okay, so the divergence is going to be positive in the first and third quadrants. All right, and of course, so the divergence will be negative in the second and fourth quadrants. Okay, so there's an example where we don't actually have the vector field given to us, so we can't explicitly calculate the divergence. So we have to do it graphically. Okay. Now I mentioned inflow and outflow before. The divergence of a vector field at a point P may be predicted by considering a closed surface surrounding the point and analysing the flow over the boundary. And the divergence is given by the outflow minus the inflow. Okay? All right, so with that in mind, let's have a look at the following diagram. So you can see here a circle has been drawn around the origin, and if you look at the vector field, there's only outflow over the circle, right? So you would think that at the point, say, 0, the divergence would be positive. Okay? If we move down to here, you'll see, yes, there is some flow into the circle, but there's a greater outflow because the magnitude of these vectors down here are much larger than the magnitudes here. Okay? So you would say that, okay, well, the divergence anywhere in here is positive. Now, here you've explicitly got the vector field, of course, so you can check your answer. Yeah, not only is the divergence positive, it's equal to 2. All right. Then there's a couple more examples here. You can see over this circle, there's only inflow. So the divergence would be negative. Okay? Here again, there's much more inflow than there is outflow. So the divergence would be negative. Now, in this example, the inflow and the outflow cancel each other out. Okay, so the divergence in these pictures would be 0. All right, let's do an example. All right, we're given a very simple vector field in the plane, and we're asked to draw a square centred at the origin and analyse the flow over the boundary, and then predict whether the fluid is expanding, compressing, or neither, if this vector field is the velocity field of a fluid. All right? So let's draw in a simple square with centre at the origin. Now, I've just drawn that square with, say, corners at 1, 1, -1, -1, -1, 1, and 1, -1. Okay? All right? So, on the boundary of this region, what's our vector field going to look like? Well, the vector field is pretty simple here. It's only xi. So we're not going to have any j component. Well, the j component is going to be 0. So the vector field along this side is going to have vectors that look like this. Now, on the other side, the vectors are going to have the same magnitude, but the opposite direction. Okay, and you can, if you want to, you can draw these ones in here. They'll actually not be as long as the other ones. Okay, so let's analyse the flow over the square. You can see along this edge, there's only outflow happening, right? Along this edge, there's no flow, outflow or inflow. Along this edge, there's no outflow or inflow. And along this edge, there's only outflow. So is the divergence positive? Well, of course the divergence is positive. We can work it out from that. But graphically, there's only outflow. Okay? Fluid is flowing out of our square. There's no fluid flowing into our square. Right? Oops. There is only outflow and no inflow. So the way you'll do that is just look at the flow along each side. There's outflow here, there's outflow here, there's neither outflow nor inflow here and here. Okay? Thus, the divergence of V must be positive at 0, 0. So physically, what does that mean? Is the fluid expanding, compressing, or neither at the origin? Well, it must be expanding. All right. So a pretty simple question. But of course, when the vector fields get more complicated, it's a lot more challenging. Okay. Now, what does divergence mean? What is its physical interpretation? And where does it come from? Okay. Well, I've mentioned it, but I really haven't proved anything yet. So what we're going to do in the last bit is to relate divergence to so-called flux density. Okay? So what is flux density? So for this particular picture, the flux density, it's the flow across the rectangle divided by the area of the rectangle. Okay, so what we're going to do is look at this rectangle here and look at the flow over the sides of the rectangle. Okay? And then we're going to somehow relate that to divergence and flux density. All right? So think about it. There are 4 ways fluid, for example, can enter or leave the rectangle. Well, you've got 4 sides, and it can flow over each side, basically. All right? So we're only working in the plane here, so things are nice and simple. Let our vector field have components m and n, where m and n are functions of 2 variables themselves. And what we're going to do here is look at the following vectors. Now, one way of measuring the flow out of, say, this side here is to look at the component of this vector field in the direction that's normal to the side, in a direction that is, from the inside to the outside. Okay? And to measure the flow, we just multiply this distance by the scalar component of this force. Right? Okay, so how do we do that? Well, you can think of this as being m evaluated at this point times the vector I. This vector here is n times the vector minus j. This vector here is m at xy times minus I, the vector minus I. And the vector here is n at x, y plus delta y times the vector j. Now, if these sides aren't very long, so in other words, if delta x and delta y are small, then the component of this vector times this length will give an approximation for the flow over the whole side. All right? All right. So the rate at which say, fluid leaves our rectangle, it's just the sum of the rates over the 4 sides. Okay, so we have to work out the rate over each side. Okay, so let's work out the flow over this side, the rate at which the fluid leads over this side and this side. Now, notice in this picture, I've assumed that M and N are both positive, okay? Of course, these vectors may be actually going the other way, so you may get an inflow rather than an outflow. Okay, so this is just the component in this direction, right? Well, I guess the component of this vector here times this length. And I guess I should really put approximately equal to here. Right, so that's that side. What about this side? Oh, okay, that'll be a minus sign. It's in the other direction. Okay. So that's the two vertical sides. What about the other two sides? Well, very similar. Okay, we've got that vector there, that vector there. So all right, so hopefully now you should be able to look at these bottom lines and go, hang on, is there divergence in there somewhere? Oh, let's have a bit more of a look. Well, the first term, I can divide both of these terms by delta x and multiply it by delta x. Then I've got a common factor of delta x, delta y. So I can obtain something like this. Whoops. Okay? Can you see it coming together now? What that first factor is going to turn into? It's going to turn into a partial derivative, right? All right. So with the remaining two terms, I'm going to divide and multiply by delta y. Oh, yep. So, where do we go now? Well, for small delta x and delta y, this is going to be approximately equal to dm dx. This is going to be approximately equal to dm dy. And notice I've got a common factor now of delta x times delta y. Well, that's going to approximately give you the area for the rectangle, right? Delta x times delta y. Okay. So, the flux across the boundary of the rectangle is approximately equal to this. Now remember, flux density is the flow divided by the area. So if delta x and delta y go to 0, let's... So it's the flux across the rectangle boundary divided by the area of the rectangle. Okay? So, letting delta x and delta y go to 0, we obtain the divergence. Okay, so that is the derivation of divergence. That's where it comes from. And that's how it measures expansion, compression, and so-called flux density. Okay, so I've still got a couple more minutes, so I'm actually going to go back and prove one of these identities. I'm going to prove the product rule. Aha. So anyone still going on this one? Anyone? Anyone? Okay. So, I'm going to prove the product rule. So imagine that we have a scalar field and a vector field. And you want to take the divergence of the product of the two. Okay? So it's quite easy to do, actually. Just a little bit annoying. Now, this phi is just multiplying scalarly, in a scalar fashion, with f, the vector field f. So it's just, oops. Now note that phi, f1, f2, f3 are all functions of x, y, and z. So when we take our partials here, we're going to have to produce some sort of product rule, right? All right, so I haven't written the arguments in, but we need a product rule here. Okay, so that's going to be the first part. Second part. Oops. Okay, and the third part. So now what we want to do is sort of team things up and try to get the right-hand side of our identity. Just so remember, we're trying to produce this now. Okay, so what have we got? I can take a common factor of phi out. Here, here, and here. Right? And on the other one, I've got a dot product. Okay, so if you look closely now, you've got the divergence here. You've got the dot product of the vector field f with the gradient of phi, right? Okay, sometimes it helps if you put brackets in. Okay, it clears up the notation. Okay, questions, Comments? Observations? Divergence. New type of derivative. Have fun with it. In the next lecture, we'll look at the curl, which is another kind of derivative. But it's different to divergence because it spits out a vector field at the end. And loosely speaking, it measures rotation. It doesn't measure flux or flow or expansion like this one does. It measures rotation. So I'll see you all next week, and have a good weekend.